Hello everyone, and welcome to EckMath. I'm Mr. Eck, and today we're taking a look at sequences, recursive sequence, and series or sigma or summation notation. There is a companion note sheet that goes along with this video. If you need a copy, just drop me a line. I would be happy to send you one. And with that all said, let's get right into it. So what is a sequence? Informally, we would say that a sequence is an ordered list of numbers. So the ordered part is important. Here's an example of such a list. 2, 4, 6, 8, 10. The list can be finite like this. It can stop exactly right here. But many times sequences have lots of terms. So say the sequence had more terms, but we didn't want to write them all. You can see the pattern here is it's listing the even numbers. So we could imagine it goes 12, 14, 18. What you might do is write a comma and then write a little ellipses, 3 dots. Write another comma, and then pick up wherever you wanted to resume. So maybe we wanted to start counting again at 32. We'll skip a couple. And 34, and we could continue like that. Now, sometimes sequences also are infinite. They have infinitely many terms. They don't have a final term. In that case, you can just end your list with 3 dots again to show that the sequence is finished, or never finishes. Sometimes you put sequences in braces to show that it's a set of numbers, although this is not really strictly required. The order part is important. The sequence 6, 2, 4, 10, 8, for example, is not the same as the sequence we listed above, even though if they were sets of numbers mathematically, we would consider those, at least the first 5 numbers, to be the same set of numbers. The sequences are different depending on the order. Formally, a mathematician would say that a sequence is a function. Surprise, surprise, in pre-calculus, we're looking at something that's a function, where the domain of that function is the natural numbers. That is, the natural numbers go 1, 2, 3, 4, etc. So what does that mean in practice? Like, why do we talk about this as a function from the natural? Well, think about our sequence before. We had the terms of the sequence, 2, 4, 6, 8, 10. And each term had a term number. This was the first term, so this was kind of, you could think about it as being paired to the natural number 1. This is paired to the natural number 2. This is paired to the natural number 3. This is paired to the natural number 4, 5, etc. You could think about this sequence if it continued on. You might have the nth term, and that would be paired to the natural number n. We talk a lot about finding the nth term of a sequence because we want to be general. And we don't use x. We would never find the xth term of a sequence because our domain is the natural numbers, and so n here stands for number. One of the most confusing parts about working with sequences is the notation, how we write things. So let's go over some of that now before we get too deep into the examples. We usually give sequences names with lowercase letters. A is very common, so you might have sequence A, you might have sequence B, you might have sequence C, etc. If we have this A with a subscript n in set brackets, this is talking about the entire sequence. So this is maybe sequence A has terms 2, 4, 6, 8, etc. More generally, we might say that the sequence A has terms A1, A2, A3, A4, etc. What the heck is A with a little subscript 1? Well, A sub 1 is the first term. A sub 2 is the second term. And if the sequence continued on for a very long time, eventually you might get to the nth term. And we would write that as A sub n. So this is the nth term. Generally, you see that little A sub n without the brackets, and it's talking about the nth term. And usually it's paired with a rule. So you might see something like A sub n equals 2 times n, which happens to be the rule for our sequence above. That you can take if the fifth term, multiply 5 times 2 is 10, that's the fifth term. N would match to 2n by this rule. So A sub n is often paired with that rule for the nth term. we'll say rule. And another thing you're going to see in recursive sequences is something with an a sub n minus 1. This is not saying subtract 1 from the nth term. This n minus 1, see how it's all in the subscript? Means that this is the term before the nth term in the sequence. And I didn't write it here, but you could also have something like a sub n plus 1, which is the term after the nth term. So this is a way for us to talk about a certain term and the term before or after without knowing exactly what those terms are and just kind of being more general about it. Well, I'm tired of being general. Let's do some specific examples about sequences and how you might see them and how they're notated. So a problem will usually ask you to list some terms. Maybe it will ask you to find the 50th term. There's a lot of different ways the questions could ask. Here, we're just going to practice listing terms. So list the first 5 terms of the sequence a sub n, and so here notice they're using the brackets to refer to the sequence as a whole. If, and they're saying an, so this is the nth term, has the rule 3 times n minus 1. Okay, so we always start with n equals 1, and we do 3 times 1 plus 1, which is 2. We're listing 5 terms, so we'll go in n equals 1, n equals 2, n equals 3, 4, 5. 3 times 2, and then this will be 3 times 2 plus 1 is 3. 3 times 4, 3 times 5, and 3 times 6. And let's simplify it and write it as a list. So 6, 9, 12, 15, 18. And since it said list the first 5 terms, we're done. That's really it for listing the terms of a sequence. You always start counting n equals 1 because that's the first natural number, and then you keep going unless the question asks you to do something different. All right, let's look at a slightly more advanced sequence. We have the sequence here b sub n. So again, we're using a different letter to talk about the sequence. This is expressing the name of the sequence, and here we're saying that here's an expression for the general rule. Now there's a lot more going on in here. There's some exponents. Let's take apart the pieces. This negative 1 to the nth power, let's think about what happens when you take a negative and you bring it to different powers. Negative 1 to the 1 is, of course, negative 1. Negative 1 squared is 1. Negative 1 to the third is negative 1. Negative 1 to the fourth is 1. So this term, a negative to a power, is going to have a really neat property that it's going to cause the sequence to alternate. And then the other piece of this expression is we have something squared. So we're going to have a sequence that's not growing with a constant difference. It's going to grow, bigger and bigger over time. But we can still do the same thing. So here, I'm going to list the terms of the sequence, and I'm just going to list, make almost a table. We can say here's n. We're going to do n equals 1, 2, 3, 4, and 5. And then this is going to be, we'll show the work for the first one. So this is going to be negative 1 to the 1 times 1 minus 1 squared. Oh my gosh, that's just 0. Okay. The next term, it's going to be negative 1 squared, which is just 1, and then times 2 minus 1 squared, which is also just 1. So this is going to be 1. All right, for the third one, we're going to have a negative to a third power, so the answer is going to be negative 1 to the third, and it's going to be times 2 squared, so that's going to be negative 4. This is going to flip to positive, and it's going to be 3 squared, so it's going to be 9. So we have 0, 1, negative 4, positive 9, and then this one should be negative, because negative 1 to the fifth, 16. 5 minus 1 is 4, squared is 16. So we have this sequence where it goes 0, 1, negative 4, 9, 16. And I guess if I had more space, we'll put it over here. We could write the answer as a list, 0, 1, negative 4, positive 9, negative 16. And so what I wanted to show you with this one is this trick of using a negative with an exponent is a great way to get a sequence to alternate, which is a pretty common thing you see in sequences. They go back and forth between the positives and the negatives. Let's look at another example. We've got sequence C down here. And sequence C has our friend, the factorial. This shows up in sequences a little more in calculus. There's something really interesting about E and factorials and sequences that we kind of come to. So here we just want to remember what factorials do. Let's go bigger. 3 factorial is the product 3 times 2 times 1. That's it. It means multiply all the numbers down. And if we have fractions of factorials, like maybe we have 7 factorial over 5 factorial, you can think about it as 7 times 6 times 5 times 4, 3, 2, 1, over 5 factorial, which is 5, 4, 3, 2, 1. And when you're dividing factorials, you notice that almost everything often cancels, in some way or the other, or reduces to 1. And so 7 factorial over 5 factorial is really just 7 times 6, which is 42. And so factorial expressions are really easy to compute. Well, not always. Often they are easier to compute by hand than in a calculator, because your calculator starts dealing with these really big numbers when a human's doing it, and they can just kind of cancel intelligently. So let's write out the terms of this factorial sequence. And thank goodness, this is only asking us to write out the first 3 terms. So let's go ahead and write the terms, and then let's simplify it. So again, we're going to do n equals 1. So this is 2 factorial over 0 factorial. Ooh, let's talk about that later. Then if n is 2, this is 2 plus 1 is 3 factorial over 1 factorial. Ooh, yeah. And then it's going to be, we're going up by 1, so 4 factorial over 2 factorial. Okay, let's simplify the terms. Again, this is kind of an advanced one, but factorials are important to remember. One fact about factorials is that 1 factorial is just equal to 1, and so is 0 factorial. So both of these denominators are also equal to 1. 0 factorial, you think it's equal to 0, but it's not. It's just equal to 1. So the bottom is equal to 1. The bottom, not the whole thing. So then the first term, if we write it, is just 2 times 1 over 1. The second term is 3 times 2 times 1 over 1. And the last term is 4 times 3 times 2 times 1 over 2 times 1. And look what those will reduce out. So our terms are going to be 2, 6, 12. So you probably will have to do some sequences with factorials. Don't get scared, don't get upset. They're just one of the math expressions that finds its way into sequences from time to time. Here's a fun fact about factorials. They're really big. So from our book, you can see that the factorials start small. 0 factorial is 1. But even by the time you get up to 7 factorial, it's 5,000. And then by the time you get up to 14 factorial, double that, you can be like, it's not going to be that big. It's at 87, not million, but billion. So factorials are very, very large. It's a great way to get an overflow on your calculator. They will quickly produce numbers your calculator cannot handle. And here, this fun bird has a great fact for us, that 10 factorial seconds is exactly 6 weeks. And I'm going to leave that up to you to double check, but just think about why that might be true. And it's kind of neat. Gives you a sense of exactly how big factorials can be, just 10 factorial. So there's also another type of sequence definition, and it's called a recursive sequence. These are easy to mix up with the types of sequence we've been doing, but they really behave completely differently. A recursive sequence is a type of looping sequence that builds the next term based on the previous term. Sometimes when you're writing the expression for a sequence, you might start with a recursive sequence because it can be easier to see the pattern, and then work towards finding a more general equation like we were looking at up here. So here's an example in words of a recursive sequence and kind of what it might look like. It might say start with n equals 3, and then to get the next term in the sequence, multiply the previous term by 2 and subtract 1. So you might say, okay, 3, and then the next term is 3 times 2 minus 1, which is 6 minus 1, which is 5. Then the next term, you would use not 3 again, but you would use 5. And you would take 5 times 2 minus 1, and you would get 9. And then the next term, you would take 9, and you do 9 times 2 minus 1, and you get 17. And then the numbers are getting large, but that would be the way to find the terms of this recursive sequence. So it's like a nice way to see how things are growing. You might notice that this term sequence it seems to be growing more and more over time, so it's probably not a linear sequence. Maybe it's quadratic. Maybe there's a power of 2 somewhere in there in the closed form. How do we write this in formal math notation if we don't want to write a whole sentence? Well, we have to include two things. We have to include the starting term. We have to say, where are we starting? So the way we do that is we just say a sub 1 equals, and we say what the term equals. So remember, a sub 1 was our notation for the first term. And that's the starting term, a sub 1. And then we have to include a recursive rule, and the recursive rule is going to say something like a sub n, which is the nth term, is some function of the previous term. And our notation for the previous term was a with a subscript n minus 1. So we're going to have this a sub n minus 1 in our definition. And so here, the rule was saying take the previous term, a sub n minus 1, multiply it by 2, and subtract 1. So that would be how that recursive rule would be written. 2 times a subscript n minus 1 minus 1. I added these parentheses for clarity. You don't need them. The book won't use them. But feel free to add them in. They're free. They don't cost you anything. And it helps to see the patterns. All right, so let's practice using a recursive sequence. This says list the first 5 terms of an if a1 is 2 and an is 2, an minus 1 minus 1. Hey, that sounds familiar. But I wanted to show you this one because it's interesting to see what happens when you have a different starting term. So in this case then, a1 is 2, a2 is 2 times the previous term, which was 2 minus 1, so that's going to give us 3. a3 is 2 times the previous term, which was 3 minus 1, 5. And then how many times we're doing? 5 terms. So a4 is 2 times the previous term, 5 minus 1. Okay, that's 9. And a5 is 2 times 9 minus 1, which is 17. So if we look at the terms, here we used 3 in that. Here we used 5 in there. Here we used 9 in there. And if we were to keep going, we would use 17 in the next definition to find the 6th term. And we kind of got the same terms, but notice it's not the same sequence. This is the sequence that goes 2, 3, 5, 9, 17. So it starts in a different spot and has different numbers of terms. Changing the starting term changes how the rule, changes how the sequence goes, which is why in any recursive equation, it's not good enough to just state the recursive rule. You also have to state the starting term. Going to the back, we're going to take a look at what happens if you have a sequence and you want to add the terms. So instead of the sequence that we had at the start, 2, 4, 6, 8, 10, what if I wanted you to do 2 plus 4 plus 6 plus 8 plus 10? Well, there's a really convenient and easy notation for dealing with that as well. So here's the example. Take the sequence where an is n plus 1. Really simple sequence. Find the 2nd through 5th terms and add these terms. Okay, we could do this right now. Let's do it. The 2nd term would be 3 because it's n plus 1. So then 2nd, 3rd, 4th, 5th. So this is like our n, and this is like our term. The 3, 4, 5, 6. And then this is to add these terms. So we'll just add 3 plus 4 plus 5 plus 6. 3 plus 4 is 7. Plus 5 is 12 plus 6. So this should come out to 18, hopefully. Okay. So how would a mathematician write this? Mathematicians don't like to write sentences. Mathematicians like to write symbols. A mathematician would write this using something called sigma notation. So they're going to use this big thing, and you've maybe seen it around in math classes. I don't know, it's like a famous math symbol. Today we get to learn what it means. First note, this symbol is called a Greek letter sigma, S-I-G-M-A, and sigma is a Greek letter S, not an E. It's an S, and that's because it stands for sum. So the sigma is a command to add some terms. That idea is it's a computer command. Command to add is a very important idea. That's like a great way to think of sigmas. So what are the different pieces? Let's zoom in on this little guy, and this is actually asking us to do the exact same problem as we just did on the right. Well, the first piece is what I would call the thing inside the sigma. This is called the summand. Summand. And it's what to add. So this is like the equation that you're adding. Then there is this variable I, and you see it in two places. You see it at the top and bottom. This is called the index. And this is just telling you what the name of the variable is. So when you see I as part of the index, and it's I because it stands for the word index, then there will usually be an I, not always, but usually an I in the equation that we're going to plug numbers into. So we're going to plug numbers in to this I in the equation because I is the name of our index. The 2 is called the lower limit of summation, or casually just the lower limit. And the 5 is called the upper limit of summation, casually just the upper limit. And so you read this as saying, start at the lower limit, start at I equals 1, add the summand I plus 1, and this will change depending on the problem, until I equals 5. So if we start at 1, then we go 1 plus 1 is 2. Then we go I equals 2. 2 plus 1 is 3. I equals 4. No, I equals 3. 2 plus, that's going to give you the term 4. 2. I equals, wait, hold on. I got to write this in. I equals 1. I equals 2. I equals 3. I equals 4 will give you the term 5. And then I equals 5, we're plugging 5 into I plus 1. 5 plus 1 is 6. We have 2 plus 3 plus 4 plus 5 plus 6. Aha. And I'm finding an interesting mistake, and I'm just going to leave this in the video because I didn't do it on purpose, but I think it's a beautiful thing that happens. In our example on the left, we found the second through fifth terms. Now, cautiously, that gave us 4 terms because we had the 2, 3, 4, and 5, so the second through fifth terms. Here, we plugged in I equals 2 to 5. Look at how many terms we had. Oh, no, I'm wrong. I actually just started at the wrong I. We did have the correct number of terms, but that's why you have to pay attention to your lower limit of summation. If I is 2, then we don't want to use this first term. We want to start with I equals 2, and then we're doing 3 plus 4 plus 5 plus 6, which is the same thing we did on the right side, so we could say this then evaluates to 18. Let's do some practice. See, that was a little messy. All this sigma stuff gets a little better with practice. So the first sigma is a sum of squares. So we have a sigma. It's saying start with I equals 1. The index is I, by the way, still I, so check that. Index is I. We're starting with I equals 1 and ending with I is 4. When you're first starting out, it can be nice to just make a table of values. So I can go I, and we'll go 1, 2, 3, 4. And then down here, we're going to put the summand, I minus 1 squared. Okay, 1 minus 1 squared is 0. 2 minus 1 squared is 1 squared, which is 1. 3 minus 1 squared is 4. 4 minus 1 squared is 3 squared, which is 9. We're done because we went from I equals 1 to 4. And so now we know the terms. We just have to add the terms to find our answer. This is the same as 0 plus 1 is 4 plus 9, which happens to be 14. So if you said saw something like evaluate this expression or evaluate this summation notation, you're looking for a numerical answer, and that answer in this case is just the number 14. One thing that can happen with sigmas, especially if you're doing different types of problems or more complicated problems, is they might change the name of the index. So look at this problem. We have j equals 0 to j equals 3. And look at the summand. You'll see that j is the variable in the summand. This is nothing to get excited about. It's just a different letter. It's going to work the exact same way. Sigmas like to use i's, j's, k's, l's, m's, n's, like sort of the middle of the alphabet for the names of the indices. Another thing to watch out for is that the lower limit is 0 now and the upper limit is 3. Now, if we go 0, 1, 2, 3, we're going to have 4 terms. So don't just always look at the upper limit of 3 and think we're going to 3 terms. You have to count with the index. So let's do this as our little table of values. So here we'll do j, and then we'll do j squared. The lower limit says we start at 0, and then we go up by 1. So we're going to do j is 0, 1, 2, and 3. And then we're going to find j squared. 0 squared is 0, 1, 4, 9. Okay, so interestingly, this also comes out to 1 plus 4 plus 9 plus 0, which is also 14. And that's one of the things that I like to share with students about sigma notation and summations, is you can have what is effectively the same problem written in multiple ways, depending on how you arrange your indices. Sometimes you might see a pattern and you might want to approach it this way. Sometimes you might see a different pattern, even if the answer is the same, and you might want to write it this way. There are usually multiple answers to any given sigma notation problem, or multiple ways to write the summation notation for any given problem, even if they have the same answer, in this case of 14. Okay, let's look at example 7. This is the sum of a constant term. So our index is I. We're going from I equals 1 to 10. Okay, so we can even start our table. We can say I, and we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll just write them rest together. But then let's look at the index. Be really careful here. This is not for I. It's not saying do 4, 8, 12, 16. That's not what it's saying, because it doesn't have that letter I there. There's no index, so this is just a sequence that is always the number 4. Don't be fooled. So the terms of this sequence are 4, 4, 4, 4, 4, 4. Now you could add up all those 4s, but what I notice is that if we wanted to do 4 plus 4 10 times, it's the same as 4 times 10, or 40. So if you see a sum of a constant, you can think about all the terms, but really you just need to multiply by how many terms there are, and there are 10 numbers between 1 and 10. So sums of constants can be tricky if you're not quite sure, but they're actually almost easier than some other types of sums. Now, you can have some really complicated sums, and I wanted to do one of these with you. Now our index is I, so let's look at example 8. And we're only going from 1 to 3, so we're only going to have 1, 2, 3 terms total as we count up. But look at the complicated terms. So we look in the expression here, and we look where is I, and the I is only up here in the exponent. What is this y doing here? Well, sometimes you have other variables within your sigma. Maybe you're adding up i's, but you have a y squared hanging out also. So here's what this would look like. You just go piece by piece. We're going to say, here's I, 1, 2, and 3. And then we just do the expression. So negative 2 to the 1, and then times y squared. This is negative 2 squared, y squared. I'm doing nothing with the y squared. We're almost treating it as if it was a constant, even though it is a letter. And then this is negative 2 to the third, y squared. And then we have to add these up. And you're like, can I even add these up? But yes, you can. The first term becomes negative 2y squared. The second term becomes 4y squared. And the third term becomes negative 8y squared. So if we do negative 2 minus 8, that's negative 10 plus 4. So we really just get negative 6y squared. And the answer in this case is not a number, it's an expression. Because we weren't plugging anything in for y, it was almost behaving just like a number that wasn't changing. What's changing in an expression like this is the index, as we count up the index. So that's one thing you might see in some sigmas. I want to share with you 2 properties of summation notation that you use all the time in calculus when you're dealing with sigmas and their related objects. And they're kind of useful to just have in your pocket. Yeah, useful to have. The first one is that if you have a summation and there's some constant multiplied to each term, usually we use the letter C or K for constant. This is not the index, this is just some number. You can actually bring that constant out. It's almost like factoring out the 3, so that instead of multiplying each term by C, you multiply all the terms by C at the end after you add them up. Here's what that looks like. Or like how that might be useful. So say I had this expression from I equals 2 to 5 of 3i plus 1. We could do this the long way. We could say I is 2, 3, 4, 5, and then 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15, and 3 times 6 is 18. And we could do 9 plus 12 plus 15 plus 18, and we could get a result. But if we use this property, we could also break this out and say that this is going to equal 3 times the sum from I equals 2 to 5. Sometimes if the index is the same, you don't write I equals on top of I plus 1. So then this is just 3 times, and this is the sum we did up at the top. So we know what it's going to be. It's going to be 3 plus 4 plus 5 plus 6, which is just 3 times the number we found at the top. I think it was 18. Oh, it's just 3 times 18, which we all know is the same as 6 times 9, 50. Just to double check that, let's add the numbers up top and see what we get. And we get 54, not 52, which agrees. So that's one way to quickly evaluate a sigma, is to factor out any constant terms. Another thing you can do with a summation notation is if you have a sum of a sum, like you're adding up something that's also adding inside, you can split that into 2 or 3 or more separate sums. So what that might look like is, say you're adding up this quadratic expression, I squared plus 2I plus 1. You could think about this as the sum from I equals 0 to 5 of I squared plus the sum, whoa, gotta wait for me, from I equals 0 to 5 of 2I plus the sum from I equals 0 to 5 of 1. Now, why would you do this? Well, maybe you already know how to do individual pieces of this, or it's easier to just find each piece. So 0 to 5 of I squared is 0 squared plus then 1 plus 4 plus 9 plus 16 plus 25. There's actually formulas for sums of squares. I think we've looked at them before. This one is 2 times 0, and then it's 2 plus 4 plus 6 plus 8 plus 10. So we have formulas for that. And then from 0 to 5, we looked at that above. That's just of 1. That's just 1 plus 1 plus 1 plus 1 plus 1 plus 1. So that all comes out to 6. Be careful, it doesn't come out to 5, because you're starting at 0. There are actually 6 terms you're adding up. And so instead of doing all of this squaring stuff, you can break it down into easier chunks, and then you still have to add the chunks, but maybe you can do some pairing of each piece. Or it's just easier to put in your calculator as multiple pieces. We have 55 for the first part, plus 30 for the second part, plus 6 for the third part, and this would all come out to 91. So that's pretty cool. And folks, that's it for today. I know it's a lot. There's a lot of different types of notation. The best thing you can do is practice. I will see you all in class. We'll do a lot more with these notations and all sorts of things. Thank you for watching. I'll see you next time. Goodbye.